call again or?
Let me just check. You can stay here. 4 minutes.
Yes, I know, but.
We shouldn't start. That would mess up my book. Can you explain us how we should fill out your form that says no, yes, no?
Oh.
I will participate. No, yes, and no.
Well, exactly. So you say no. No, but that's fine. I think everybody manage. Sometimes I have people who are not participating but are coming with 2 people, so that's fine. I can handle this. Anyway, I'm not sure we'll get the exact count for people, so I will plan 1 or 2 more. All right, so we are going to start. Just for your information, so today's speaker is Hermann, and unfortunately couldn't make it in person, so we have a video call. So for the questions, actually, I will be sitting over here, and in order for Hermann to hear well, I will repeat all the questions on the computer. So if you have questions, actually we don't need the microphone today because anyway I will repeat the questions. Just raise your hands and ask your questions. So I let Ken introduce the speaker of the day.
Hey, it's a great pleasure to introduce Hermann. I think he and I go back to Bell Labs days too, actually. He was visiting Bell Labs back in the day. I think he was only there for a year or something. I was looking at some of Hermann's most cited papers. Everybody's probably heard of Nestor and I back off, but of course nobody does n-grams anymore, so maybe they haven't. Also, I noticed a whole bunch of papers with Franz Ock, who I'm clearly not saying his name right. Maybe Hermann can explain how to say his name. But at any rate, you probably know about Google Translate. You've probably heard of that. And maybe Hermann can tell us about that. But I think Hermann's going to tell us about something else. So take it away.
All right.
All right.
Okay. I know.
Can you hear me? Sorry, can you hear me? Can you hear me? Yeah, but the sound quality on your side seems to be, at least for me, seems to be very, very bad. So I have really problems understanding you. Maybe it's the echo or so. I don't know. This is much better. This is much better now. Okay, please. Okay. Sorry, I could hardly understand what you said before. So I'm supposed to start now? Okay. So hello to everybody. Good afternoon. First of all, I'd like to thank Sanjeev for the invitation, and I guess Ken said maybe a few words about me. I'm not sure, so thank you very much. It's a pity that I cannot join the workshop in person. Those of you who know me know that I really enjoy being in France, so that's really a pity. Okay, so speech and language technology from small to large language models. Now, of course, nowadays it's not only the language models that are large, but also the other models. But language models seem to get most of the hype. So what I'm going to talk about is based on my personal experience. There are some messages that I want to get across, like what is a unifying framework for what we are doing? And that's, in my view, the framework of probabilistic modeling and based decision theory. And in particular, I would like to convince you that deep learning is a very successful method, but it's just one out of many possible machine learning approaches. And in particular, we have seen the evolution from rule-based to data-driven approaches for the last 40 years. And at the same time, it was an evolution from small to large language models. And also, what I would like to stress, things started not just a few years ago, but already 40 years ago. So my experience is based on sequence-to-sequence processing tasks like ASR, handwriting recognition, machine translation. In all these cases, we want to generate a sequence of words in natural language. So that's a common characteristic. And if you really want to produce the best results here, then typically we have to use a language model, which you might call small. And the task of this language model is to make sure that the output that we generate is really smooth, fluent from the viewpoint of syntax, semantics, context, and what have you. So nowadays, this is referred to really as generative aspect of a language model, in contrast to other NLP tasks like parts of speech tagging, syntactic analysis, semantic role labeling, and what have you. Here, really, the output is some specific, let's call it NLP text, NLP formalism, as opposed to text of natural language. And this was really the starting point for language modeling. They were used to make sure that the output of these systems was well formed from a syntactic, semantic, maybe also pragmatic point of view. And the advantage of a language model is it can be learned from text only. So this is referred to nowadays often as unsupervised mode because there's no annotation needed for the text. I think this term is confusing, but that's the terminology nowadays. And it's also referred to as pre-training because this training step might be followed by more sophisticated training procedures. In my view, all this started with speech recognition in the 70s of the last century. So we have sequences at various levels. We have the sequence of acoustic vectors. We have the sequence of phonemes that we want to generate, recognize, the sequence of words that results then in the output sentence. And we have ambiguities at all levels. We cannot recognize the phonemes very well. We don't know where the phoneme boundaries are, the same with word boundaries and so on. So we are faced with that problem. In addition to that, there are interdependencies of the decisions at all these levels. And then it was Fred Jelinek and Jim Baker who suggested, okay, all this should be handled by a framework of probabilistic modeling. In particular, we should use a holistic approach, which nowadays you might interpret as end-to-end. We should have a single criterion for system design, which again, typically in machine learning, pattern recognition in those days was referred to as a base decision rule, and that will also be the term I'm going to use. So at that time, this concept resulted in complex mathematical modeling. I mean, complex, that was what was it considered to be at that time? If you look at our models of today, then they are far, far more complex than what was considered to be complex in these days. So let's start with some technical details. We're looking at a sequence of acoustic vectors over the time axis. We want to generate a word string over word positions n. Then at that time, the starting point was to say we're looking at the joint distribution of output sequence and input sequence. And we do this factorization into a language model, which then can be learned from text only. At that time, it was basically word trigram counts based on word trigram counts. And then we have the acoustic phonetic model, which has to be learned from annotated data, pairs of audio input strings and text output strings. And the method favored at that time, and that turned out to be most successful at that time, was really generative hidden Markov models. In the beginning, discrete models with vector quantization, later on Gaussian mixtures with some more refinements. The characteristic property of these models is that we have first order dependencies. which results in nice mathematical aspects. So we have a nice efficient trading procedure that was referred to, it's still referred to as EM algorithm, which has closed form solutions within each step of the EM iterations. So now when you analyze the history, that at that time there was really a dichotomy. There was the area of general machine learning, like object recognition, computer vision, where people looked at single isolated events, let's say input vector or the whole image, and then the object label, single object label. And it was clear from the machine learning point of view that it's better to use a discriminative class prior approach based on this quantity, class posterior probability, rather than some generative model either based on the joint probability or on the class condition probability. But then in ASR, we said, okay, this is sequence to sequence. This is different from the general machine learning problem. We have to face time alignment problems, synchronization problems, language model context. And so there was an emphasis on this generative joint model that I wrote down here. And then decoding is still based on base decision rules. So when you put everything together, this is what we are getting. And here we have these different knowledge sources. So there was already a separate language model at that time. And the model architecture here was, let's say, the starting point for the Tangora system, which was an operation research system around 85, introduced by the IBM team, or built by the IBM team, 5,000 words at that time, isolated words, so you had to make clear pauses between the words in order to simplify this search problem, and it was speaker dependent. And of course, it was complex in the sense that it was at the limit of what could be done in those days using the existing computer hardware. I myself got involved in this area when I started working at Philips Research. We started with 1,000 word recognition, and then we built a 10,000 word system. This was continuous as opposed to the IBM system, and really resulted in a commercial product. We put a lot of effort at that time into optimizing dynamic programming beam search, so that we had a real-time operation on a Motorola 6020 processor. Then later, when I joined the university, I got involved in a couple of research prototypes for speech translation. Typically, these were cascaded systems, ASR plus MT, Workmobile, which was sort of toy task, and then TC Star, which was, I think, the first research prototype that was built for real-life data, sort of unlimited domain. So it was about the speeches given in the European Parliament. And we used statistical MT in order to have a system that was robust with respect to ASR errors. So that was fully automatic at that time. It was not real time, but it was without neural networks, without deep learning. And maybe just 1 minute of a demo that we had at that time. Did I lose it? Oh, where is it here? Okay.
Gracias, señor presidente.
Can you hear it?
Este informe que hoy debatimos sobre el modelo social europeo para el futuro, del que sobre todo quiero destacar el consenso que se ha logrado entre los dos grandes grupos políticos, y quiero felicitar expresamente a mi compañero José Silva y también a Pioners de Rosa por el esfuerzo realizado, constituye una buena noticia porque está llamado a contribuir a la solidaridad.
Okay, that should be sufficient. So that was nearly 20 years ago, fully automatic, without deep learning, but not real time. And then later we got involved in a couple of DARPA, IARPA funded projects, and also large-scale European projects, also French project, Quero, and so on. Okay, so there was a steady improvement of these methods, Gaussian hidden Markov models and extensions, speaker adaptation. There was an important methodology that was introduced in those days, namely standard public data, so that comparative evaluations can be done, and that was really favored by NIST and DARPA. And in these evaluations for speech recognition, the generative HMMs and refinements was the method that turned out to work best. But there was one exception, that was Tony Robinson in '94. He used what is nowadays referred to as hybrid HMM. and the underlying neural network structure was a RNN. But this wasn't a singularity. He left the university and nobody took up his work. And then there was also some criticism about this data-driven approach in these days. The criticism was, okay, these systems need too many parameters, there's saturation, there's no improvement anymore. And at the same time, we have lots of knowledge about speech, phonetics, language structures that you can find in textbooks written by phoneticians, written by linguists, computational linguists, and this should be used for speech recognition. None of these concepts was really successful. There was also the concept of support vector machines. You might call this is a data-driven approach. Again, this was never successful in my interpretation. Maybe that's controversial, is these support vector machines are not really good in modeling in modeling true distributions, good distributions. So it's difficult to combine these distribution outputs when we have to model a sequence. Okay, so short history of the first approaches to ANNs in acoustic modeling. In particular, I would like to mention the work by Hervé Bollard and Christian Wellekens. They showed that the ANN outputs can be interpreted as glass posteriors, and they advocated hybrid HMM. We should use an ANN in order to generate frame label posteriors as opposed to observation probabilities as they were used in classical HMMs. And this was also the concept that was used by Tony Robinson, whose system I mentioned already. Then there was John Bridle, who showed that we can compute the posterior of a Gaussian model. We get the softmax, and the softmax is one of the key operations that is still used in neural networks today. Then I'd like to mention Patrick Hafner. He presented an approach that nowadays would be referred to as sequence discriminative training for neural networks. The real first operational system, or only system that was built in those days, was a system by Tony Robinson that I said already. It was really competitive in the DARPA evaluations. There was another direction how we could use neural networks in speech recognition. This approach said we could use ANNs for feature extraction, and then this can be followed by a Gaussian HMM. This was referred to as tandem HMM. And my team really also started working with this concept. Later on, we switched to the hybrid one. And then 2009, there was Alex Graves. He presented, let's say, systems that outperformed the competing systems in this ICTA competition of 2009 on handwriting recognition. So there were two operational systems long before, let's say, what is considered to be the neural network revolution already a long time ago, 94 and 2009. Two operational systems that were really competitive, and in the case of Alex Graves, it was really much better than the competing approaches. Okay, I skip that. So let's look at technical details. I like to prefer the view that we are faced with a two-dimensional problem. Here we have the sequence of input vectors over the time axis. Here we have a sequence of states or segments, and each state or segment is associated with a label, phonetic label, card label, graphemic label, so that the sequence of these labels defines the word sequence, the output word sequence. And then the classical HMN can be formulated in this way. It tries to compute the distribution, or distribution density to be exact, over the sequence of observed acoustic vectors, hypothesizing a certain sequence of labels. Now, we do not know the path that we have to select within this finite state machine. So from a probabilistic point of view, we have to sum over all these paths. Then along this axis, we do a factorization. And then the contributions are the transition probabilities and the observation probabilities. What is the probability of observing an acoustic vector at time t, assuming that we are in state S with label A. Is phonetic label, card label, whatever, A. Now it was Bollard and Christian, Hervé Bollard and Christian Wellekans that pointed out that instead of modeling this quantity, it's much better to model this one from a machine learning point of view, because this is a distribution density over continuous valued high-dimensional vectors, which is difficult from a machine learning point of view. This is just a distribution over, I don't know, 100, 1,000, 2,000 discrete labels, which should be much easier. And then when you put everything together, you find out that we compute this posterior probability. So given the acoustic observations, what is the probability for any possible associated sequence of labels or word sequence, if you like? And all these things were known already 30 years ago. So you can ask the question, what is really different now after 30 years? I think we have just learned how to handle a complex numerical optimization problem. Of course, in order to do that, we need more powerful hardware, which was not available 30 years ago. We gained a lot of experience about how to achieve convergence with these complex models. There are a lot of recipes nowadays. And as a result, we are able really to handle deep multi-layer perceptrons, and then we could move on to RNNs, attention transformer, and so on. Okay, let's look at an alternative to the transducer. So far, I talked about, well, I did not say that, I should have said this. At this time, in the 90s and before, this was referred to as hidden Markov model. This was really a probabilistic finite state transducer. And in this category, we also find CTC transducer or RNN transducer. There's no real difference in my view. The only difference is that here in these cases you add, or you have a different interpretation of the labels by introducing epsilon transitions for the epsilon labels for the alphabet of labels of your label posterior models. So here you allow for epsilons, and this is what makes the difference for CTC and transducers. Then again, differences come in whether you have a dependence on the predecessor grid point here or not. But the general formalism is still the same formalism as for hidden Markov models. But there was an important alternative, attention or cross-attention, so as introduced by the Benjo team. So here the concept is to say, okay, we do not handle these input vectors directly. We compute some representation, some state vectors. We do the same for these output labels. We have also some internal representations. And then the key question is, how do we find the association? How do we relate the observations along this axis to the output label that we want to generate in this position S? And in order to do that, they do a direct factorization of this quantity over this axis, the states or segments, if you like, and then they make additional, there are additional assumptions. In particular, they introduce a context vector, which is obtained by averaging over all internal representations along the input axis using some weights that are computed in a specific way. As opposed to that, in the case of finite state transducers, we say, okay, we have these hidden alignments that we don't know, and then we factorize over this axis and do a decomposition, and then we have this quantity which might be further decomposed into transition and emission probability. These concepts have been covered in a couple of papers by my team that were presented at ICAST and Interspeech. Now, of course, an important refinement of the cross-attention approach is the transformer approach. So the idea is to keep the principle of cross-attention between input axis, input stream, and output stream, but then to say, in order to compute these internal representations for input or output, we use self-embedding rather than RNN structures as they were introduced originally for the attention approach by the Montreal team. And then, of course, we have several layers here to compute these self-attentions. And then OpenAI went to extreme position by having nearly 100 layers here. That maybe also here in the cross-attention part. In that context, I would like to bring up work that was done by Kaltenbrenner and his colleagues and Sutskever about 10 years ago. They said the MT problem can be handled by a language model approach. We merge these input-output sequences into a single stream. So input sequence, output sequence, input sequence, output sequence as a single stream. And then we handle this like a language. We handle this as like a language model problem. And this is the concept for the GPT approach, which is very successful for many NLP tasks, generative tasks in particular, and tasks that go beyond MT. So maybe some words about MT itself. I guess some of you are young and maybe they're not aware of the fact that the use of data-driven statistical methods in MT or in general NLP was rather controversial in the past. And it goes back to Chomsky's views. The notion probability of a sentence is an entirely useless one under any known interpretation of this term, and he made many statements like this. He was very successful with his Chomsky hierarchy in what is nowadays known as Chomsky hierarchy for formal grammars. So he was considered to be a Pope authority, whatever. And so the mainstream, in the mainstream research in speech and language was a strict dichotomy. We had the speech area. Here people said this is signal, sub-symbolic processing, machine learning. Then language, this is written text. Here we have to handle symbols, grammars, rule-based AI, and so on. So until 2000, the approaches to MT were, the mainstream approaches were rule-based. A huge human effort is required to write down all these rules, in particular to make sure that they cover all possible situations and they are not too much inconsistent. The IBM team, at the end of the 90s, they started a statistical approach to MT. Their system in the end, if I understand correctly, had a performance that was comparable to what the rule-based approaches had in those days. Key people here were Bob Mercer and Peter Brown. They left 94 for a hedge fund, and so IBM stopped working on that. When I started at the university, I added machine translation to the area that I had been working on before, speech recognition. And at that time, there were, as far as I know, only 2 teams in the world that really advocated the use of data-driven methods for fully fledged MT systems. That was Enrique Vidal in Valencia in Spain. That was Dekai Wu, ICSI in Berkeley, and later, I think, Hong Kong University of Science and Technology, and my team. And we were able to do some improvements beyond IBM's approach, like HMM alignments, log linear modeling, phrases as basic units. And this turned out to be, let's say, helpful. And so around 2004, this data-driven approach changed from a singularity to mainstream, in particular when Franz Ochu was one of my first PhD students on MT, joined Google. Later, some more of my PhD students followed, and in 2008, they introduced the service Google Translate, or to be more exact, they replaced the existing rule-based approach, which used Systran technology. They replaced that approach by a data-driven approach. And then around 2014, Neural MT came out, in particular, the attention mechanism as introduced by the Benjo team. So, how am I doing in time? So I still have 25 minutes. So far, I just summarized the history, but what are the underlying, let's say, what is the unifying framework for all what we are doing, that brought improvements? I think in order to understand that, in the end, we have to look at performance, and in order to do that, we have to revisit base decision rule and its framework. I think this framework is more or less covered in a book that came out already 40 years ago, Duda and Hart. But at that time, what he wrote down, or what they wrote down, was not explicitly meant for string processing or ASR. And in my team, we try to do work along these lines. How can we do let's say, a well-motivated statistical Bayesian approach to ASR. What can we say about training criteria? In order to do that, we really have to study the mathematical details of the whole approach. And this is some work we did. And this resulted also, in my view, in some practical implementations for training criteria. So I try to give a short summary without going into details. So we are looking at input string, simplify notation, just X is now a full string and C is the output string. We need a performance criterion, which is then defined, which typically results in a loss function between the string that is correct and the string that is recognized, for example, edit distance in ASR. Now the true base decision rule says, okay, we get the best performance if we want to guess the class C or the output C from the input string X by doing this operation. We compute expected loss using the true posterior distribution, which might be difficult to know, but when we imagine a huge amount of data, limited, huge but limited, then we can, at least conceptually, we can imagine we can compute this posterior probability. Then we can compute this expectation of the loss function for each hypothesized output string C, and then we can find the output string that minimizes this expected loss. Now then we say, oh, unfortunately, we don't have the true distribution. Let's put in a model with parameter theta, and then the rule looks like this, but this, strictly speaking, at least when you talk to a statistician, is not a base decision rule. You can call it pseudo-base decision rule because we do not use the true model here, and the expected loss now is based on our model. And also in most textbooks, the starting point is not a general loss function, but 0-1 loss, where we say this is 1 if the two strings are not completely identical. If they are identical in all positions, and if they have the same length, then the cost is 0. Then the expected loss can be computed like this, and we get this, if you like, maximum a posteriori decision rule, where we look for the string with maximum probability. So now, if you do a careful analysis, exact mathematical analysis, and a couple of questions come up. The optimality of this rule here, guaranteed optimal performance, is that still preserved when we switch from the true distribution to a model? In practice, we often use this loss function. How much does this simplification matter? And then what training criteria can we derive from this whole concept? And when I put everything together, then this is my view of what we are doing today in, let's say, machine learning for sequence-to-sequence processing. So this architecture tries to answer the question, why are we doing what we are doing? We have to agree on how do we measure performance. Then this performance criterion, this loss function, should be put into base decision rule, for which we need probabilistic models, which have 3 parameter theta that we don't know. We have to learn them, so we need a training criterion. But of course, the training criterion should reflect that we want to have good performance on unseen test data. So somehow the loss function must come in here. And one, let's say, result then of the training criterion might be a criterion like cross entropy, directly under certain assumptions or under certain simplifying assumptions. So we are faced with a complex numerical optimization problem, like, let's say, backpropagation might be one solution, one approach. So we learn these parameters, we put them into our base decision rule, then we are faced with a combinatorial problem, and then we can evaluate, then we generate the output, and then we can measure, okay, how well does our system do? So in order to do a real careful analysis, we have to strictly distinguish between the expected loss or error rate for the true distribution and for our model. There's one result which is interesting, like when we compare these two rules, yes, then you can show mathematically that they result in exactly the same output string if this loss function is a metric, and if this means mainly what we need to prove is the triangle inequality, and if this posterior probability is larger than 0.5. So if the error rate tends to be small, then we cannot expect differences. There cannot be any differences between these two rules if this is a metric, and edit distance, for example, satisfies the condition of a metric. And then, of course, the important question is, what are the conclusions for training criteria? I will come back later on to this question. So now you can ask, but okay, some of these things were known already 40 years ago. Where do we stand now after 40 years? So, as I said, the exact loss function details here do not seem to be critical, and at least when we talk about systems that have low error rates. And this might be more important in training and testing. As I said, there cannot be any difference if the posterior probability is larger than 0.5, and if the loss function satisfies the triangle inequality. Now, where we achieved most progress are really these probabilistic model, and maybe that's always the most challenging task. In particular, here we have to model the synchronization problem between input and output, finite state transducers, and attention mechanisms. These are the two concepts that I see here so far. And if you want to build the best system, again, I will come back to that, we need a separate language model, because the training data situation favors the use of separate language models. Training criterion is important, but of course, it depends very much on the probabilistic model and on the loss function that we are using. Numerical optimization is a hard mathematical problem. We have learned how to handle it, at least practically. And this was really like the improvements in modeling. These are the two, let's say, areas where we, in my view, have done most of the progress. I mean, we also have progress in search. My team, we worked a lot on search, but I must admit, nowadays the models are so good that this component is much less critical than it used to be. So the critical components, in my view, are really this one, good probabilistic models, and in practice, we need good numerical optimization. Now let's look at some more technical details. We are looking at such pairs, input audio, output string. And then the typical approach, at least in what my team is doing, is to say, okay, we are looking at this posterior probability, which is written as a log linear model. We have a contribution from the language model. We have sort of acoustic model, and we do renormalization. We have exponents alpha, beta, and unknown parameter theta. Now, the motivation for this is really still the generative approach. When we talk about the generative approach, the posterior probability can be computed like this. Then we factorize this into the prior language model and the class conditional model. Now, the important step is, which let's say nobody mentions explicitly, or is maybe not known, just a small step. Instead of using this quantity here, you could replace it by what I call pseudo-posterior. You can renormalize this over all strings. So you get a normalization factor that depends only on the input. And because we have numerator, denominator, this cancels. So this can be really rewritten like this. And now we identify this with this quantity and this pseudo-posterior with this acoustic model. And in addition to introducing these components. The advantage of the language model is that it can be learned from text data without any annotation. Let's say 5 years ago, typically you used 100 million words, maybe even 1 billion. And for the acoustic model here, I wrote down the formula for transducer concept, TTC, transducer, discriminative HMM. And here, let's say, for some tasks, we had 500 hours, equivalent to 5 million words. So the relation between these two is 1 to 20. So we have 20 times as much data for the language model as for the acoustic model. In order to build the best model we can build, it's not a good idea to ignore the language model data. Now, what about training? The ideal training criterion, I do not have time to go into this, is to maximize this quantity. We go over all training pairs. We take the logarithm of the string posterior probability, and we optimize this quantity over the unknown parameters. The model is decomposed like this: language model and acoustic model. So here I look only the acoustic model has parameters. We assume for the moment the language model to be fixed because we focus on the acoustic model. Now, the complication here is the denominator. You can, in first approximation, you can drop it. Then you get a simplified baseline, which results in a system that has, at least in training, we decouple the training of the language model and of the acoustic model. And then this results in the usual criterion sum over all path in a CTC system, in an HMM, hybrid HMM, in a transducer model. And maybe as a side remark, I would like to say the M framework still works for neural HMMs, but you have to take into account that you do not have closed form solutions anymore in each updating step of the EM algorithm. Now, when we keep the denominator, this is referred to as sequence discriminative training. The concept of this was introduced already, well, nearly 40 years ago by the IBM team, and at that time it was referred to as maximum mutual information concept training criterion. Now there's a subtlety here. In reality, we are not interested in the 0-1 loss string error, but really in word error rate. Then everything gets more complicated, and you need even more approximations, like phonemes, definition of phoneme symbol error, state minimum base risk, and what have you. And in that case, we really have an interaction between the language model and the acoustic model in training. So when we do this, the training procedure for the acoustic model does not know that we are later going to use a language model in recognition. Whereas in this case, the training procedure is informed. We are training the acoustic model, but finally, we are going to make use of a language model in the recognition process. And there are various ways now to approximate this denominator. Again, work here started already more than nearly 40 years ago. So in that context, it's, I think, appropriate to say a few words about end-to-end concepts. Now, what does end-to-end mean? Does it mean we have a single training criterion or maybe also single decision criterion, a single global criterion for optimum performance independent of model structure? Or is it that we are referring to the structure of the model so that we do not really have a decomposition into these two components? And then often people argue this approach is more elegant, it's simpler, yes. But then my answer is, but what about adequacy, performance? In the training data situation is typically like this. We have 5 million words transcribed audio, annotated data, 100 million text data. Or nowadays, but this was numbers for 5 years ago. Nowadays, this might be 5,000 hours, and here we might have 1 billion, 2 billion, 3 billion words. So the relation still is something like 1 to 20, and then it's just not a good idea to ignore the language model. So I think the end-to-end concept, yes, we have to use a holistic criterion, but then the structure of the model, here's a key question, can it reflect the training data situation? And then I think we really should separate the language model. Okay, so some results about the language model that we obtained long time ago. So here we have different types of acoustic model, Gaussian mixtures, feed-forward multi-layer perceptron, LSTM, RNN, in the context of a hybrid HMM or posterior HMM, if you like. Then here training criterion, maximum likelihood. You can also do sequence discriminative training for Gaussian mixtures. Then here frame-wise cross entropy, Viterbi approximation, then sequence discriminative training. And here we have a count-based language model. So we see there's a clear improvement when we go from maximum likelihood training, sequence discriminative training, then already the starting point for the frame-wise CE system with the feed-forward multiple layer pattern is much better. Then further improvements by switching to sequence discriminative training, frame-wise cross-entropy with an LSTM, RNN, and then further improvements by using sequence discriminative training. Now this was a count-based language model. Here we have a combination of count and neural network-based language, but I'm going to say a few words about this later on. So the perplexity here is much better, and we see the expected improvements. So in total, if you look at the best neural numbers that we had in those days was 19.2. This is already neural networks. This is without a neural network. And the best one here with neural networks was 8.2. This was, well, meanwhile, 6 years ago. So there was an improvement from 19.2 to 8.2, which is 60% relative. And similar improvements were reported by other teams. Now you can ask the question, what is the relation between language model perplexity and word error rate? So here we have perplexity for a count-based model, I think it was 5 gram, 6 gram, and then a model that used an interpolated concept, a count model based on 3 billion words, and an ANN model trained on 60 billion words. And this data set was, let's say, more domain specific. I mean, these experiments were done a long time ago when we had problems with training neural networks, language models for 3 billion words. So it was an interpolated model. Here we have the perplexities, 10 gram multi-layer perceptron, recurrent NNN, LSTM RNN, and then these models with 2 layers. We see clear improvements and improvements in the associated word error rate. And in total, we get a reduction of 15% by going from models that have a 30% by using an improvement of 30% in perplexity. So you might ask the question, what is the relation between perplexity and word error rate? And this question was already considered by John McCool and Richard Schwartz, again, 30 years ago. They said in the first approximation, word error rate can be described as a constant times the power of perplexity, where the exponent is between 0.3, 0.5. Under the assumption that we always use the same acoustic model and we have no search errors. And so here you have a plot for our results. So perplexity in logarithmic units, word error rate logarithmic units. So when you do this in logarithmic units, then you expect a straight line, and this is what we are getting more or less. So this presents a good approximation. We have different types of models here, count-based models, forward models, RNNs, LSTM RNNs. So these are more models than I showed in the table before. Now this is a small range, and you might complain, well, maybe this is not true when we have a larger variation in perplexity and word error rate. So I asked my people to build low-quality language models, poor language models on purpose with high perplexity. And then we see that the word error rate goes down from, I don't know, 33 or so to 11 or 10%. And again, the relation can be described very well by this power law. And just as a remark, Google had a paper at the recent ICAST where they used really large language models in the context of ASR, like here, and they could show that they get significant improvements because this large language model had a much better perplexity than the language models that we built here that you get when you train it on such limited amounts of data. Okay, then I think I should move on to language models in particular and neural network and NLU. So there was some work already in the 90s, but on using artificial neural networks for language modeling. But I think what they did not really use explicitly was the concept of word symbol representations. This, I think, is really a key component when we use ANN-based language models. We map the discrete word symbols to a high-dimensional vector, and then we do operations, the usual neural network operations, matrix, vector product, nonlinearity, and so on, in this high-dimensional space. And then, in the end, we go back again to the discrete vector symbols. This concept was, I think, introduced by Benjo and his colleagues. It was Holger Schwenk and Jean-Luc Gauvin, I think, who produced first results in a context of a fully fledged ASR system. Mikolov extended these concepts to RNN-based language models, and we could show that you get further improvements when you switch to LSTM RNNs. Now, some people could put all these statistical models, maybe in particular these neural network models, in the context of distributional semantics. There are people that said sentences like, okay, words are similar if they appear in similar context. You shall know a word by the company it keeps. And in particular, I would like to mention the work by Colobert and his colleagues, 2008 at ICML, a unified approach for NLP, deep neural networks with multitask learning, and the follow-up paper, NLP almost from scratch. So what they were doing is they trained these word embeddings using a language model in the context of a language model, and then they added some extensions, additional layers, in order to form specific tasks. And I refer to this as formal NLP tasks, as opposed to generative tasks where you do speech recognition, question answering, speech recognition, and so on. And Mikolov and his colleagues, they showed that with these word vectors, you can do sort of calculations, Germany minus Berlin. The resulting difference vector is about the same as the difference vector for France minus Paris, similar for king minus queen on one side and men minus women on the other side. It's the same, then in 2013-14, some teams introduced this concept that you could do MT, data-driven MT, by just using a language model concept. And then this was pushed to an extreme by OpenAI, by an approach that they later referred to as GPT, architecture, and large language models. So G stands for generative, generate text, as opposed to these formal NLP tasks. P like pre-trained, based on text without any annotation, and then T, transformer, the specific transformer architecture, and now LLM, of course, more data, more parameters, multilingual, multitask, and probably more multis. There was a paper, Instruct GPT, in 2022 by the OpenAI team, training language models to follow instructions with human feedback. So the first step here is really log perplexity training, but they found out, or maybe also other teams found out, that there is a specific property that I find really surprising, and I think they also find it surprising, that you can specify the type of task that you want to do with your language model in plain language, not in formal language, but in plain language. Tasks like question answering, summarization, story generation, translation, but in all these cases, the output is natural language text. That's exactly what language models, large language models, are designed for. Fluent, smooth text. Whether this is semantically correct, that's maybe a secondary question. So the full operation of such a large language model can be described by a triplet. You specify the task by a prompt, you have the input data, and then the system generates the output data. Or you might also use these triples in order to do supervised fine-tuning. All these triples are mixed, merged into a single stream. So again, we have log perplexity training, and then the refinement is to move to include human feedback and to do reinforcement learning. I think that's the right time to stop. So I've tried to look at 40 years of building operational systems for NLP. There was success of data-driven approaches over handcrafted rule-based approaches. And what I wanted to show is the the idea started 40 years ago, not only 10 years ago. There was a persistent evolution of data-driven concepts. At the beginning, it was signal processing, speech recognition, maybe also handwriting recognition. Then it was text-based NLP, language models for ASR, machine translation, and nowadays large language models, and where the emphasis is on what you just might call generative NLU, like question answering, summarization, dialogue management, and so on. And what I think what is overlooked really is this concept of symbol embeddings, vectors, in contrast to symbol count statistics that we did until sort of 2000. That's really an important concept, and I tend to think that our colleagues in statistics that are doing statistics for categorical data, I have the impression that they are ignoring or they are not aware of these developments. And then the unifying framework for all this, in my view, is really statistical decision theory. Now you might ask the question, what about the future? Of course, like Bob Mercer said, there's no data like more data. This was at one of the IEEE ASRU workshops. I think it was 89, but I'm not fully sure. So the tendency will be more data, more complex models, more parameters, more computation that is then needed. More scientific challenges that I see are we need better mathematical framework, because backpropagation is still very much trial and error. we do not have a good theory for numerical optimization of systems with 100 billion parameters. Then the ANN structures, we select them empirically. We just find now, okay, transformers or transducers maybe are better than, or let's say transformer concepts, self-emitting concepts are better than LSTM concepts and so on. But why? So the lack of principle, in my view, mathematical justification. And also all this is done within matrix vector product concepts. This is neural network structures. And I tend to think there are more complex mathematical structures beyond the present structure. So there's life, from my point of view, outside and beyond deep learning, but it's always data-driven. And it might be even more complex mathematics. This might involve even more complex mathematics. So I said already, word embeddings. This is, I think, might be overlooked by our friends in statistics. Then what I discussed here was really supervised learning. In contrast, you might consider truly unsupervised machine learning, where we have absolutely no parallel data. Nowadays, people sometimes talk about unsupervised training, but some parts of the data, some subsets might be annotated or parallel. Okay, thank you very much for your attention. Yeah, I can understand now better. Oh, I'm sorry, I can hardly understand you. Could you do you have the microphone? Could you repeat the question? I could hardly understand. I could not really understand it. Also, I cannot hear anything. I cannot hear anything.
Yeah, can you hear me?
Oh, no, a terrible echo. Now it's better. Yeah, not much. I mean, Chomsky is, let's say, the one statement that I reported was a specific citation from one of the articles, but there were maybe statements like this before and after that. Yes. Okay. Okay. Fine. 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 Yes. Yes. Okay. But I mean, I think okay. Maybe I can. I'm not sure whether I understand what you're acoustically what you're saying, but my view of all this is computational, let's say, linguistics and phonetics. These are sciences, yes, but they are not designed, in my view. Maybe that's controversial. They were not designed to build operational systems. But what we are talking here about is really operational systems. And that brings in aspects that might be different what is considered in these disciplines. And that is, of course, I think the big controversy, whether what has been done in general linguistics, what has been done in general phonetics. Of course, it's good to know all this, but the question is to what degree it is helpful, essential to build operational systems. I mean, if you know all this, then of course it will not hurt to build operational systems. But if you try to implement exactly these ideas, then it might be more difficult for you to build an operational system. It's controversial what I'm saying, but that's my view.
I wanted to have Hermann's opinion because you have mostly introduced the history of ASR to optimize the water rate metric, but it seems that the metric itself is evolving. Nowadays, the water rate is kind of, let's say, saturated. So I'm just wondering what is his opinion, what is beyond water rate? So the question, if you can hear me, is so thank you for the presentation first. And the question is that he's arguing that the metric is actually saturating, that water rate is coming to an end, if I summarize. And he asks what you foresee to go further.
I'm not sure, again, I understand. I hear there's a question about water rate.
Yes.
And the question is whether that's already good enough or whether that's really a good, there's always room for improvement. And I tend to think what we're doing in our field is like physics. We are building models that are better approximations to nature, the nature of speech and language, as we find it outside any theory about speech and language. So our models are getting better and better. But I do not think that we're going to reach perfect models within the coming, 20, 30 years. And then, of course, I'm not sure whether that was the idea of the comment. You can question the use of word error rate as such, because it's just a word error rate better and nothing else. But of course, in the concepts of base decision rule, when you go back, you can replace the output here, really the action of the system, so that the whole framework then is not just input to output, but input to system operation. So I think there's room for extension. I guess some people must have done that already. People talk about, Markov decision processes and so on. I'm not sure whether that's, because I was not sure about the comment or question. These are my, let's say, extensions of word error rate.
Okay, I will try to write the questions in the chat, so that might help.
Yes,
also,
please. Yes,
the sound
okay.
seems very difficult. So, any other question?
So, I have a question.
Okay. Yeah. Sorry. Go on. Yes. Sorry. Go on.
So, if you can hear me, that's okay. Otherwise, Anthony will type the question. My question is, there is this feeling that these very large language models have some emergent properties that are not in their data, that they have behaviors that are sort of surprising, unexpected. What do you think about that claim? Like, do they have
Again,
Yeah.
so the question is about whether there's some, let's say, how can I put it? If you really use a huge amount of data, then suddenly large language models are getting better and better. Is that what you're referring to?
Yeah.
Yes.
Well, yes, I mean, I do not have any clear idea. I've thought about it, but I've never found anything that I can say. I mean, yes, I don't have any explanation. I do not have an answer to your question. I agree with you, but I do not have an answer. No, I don't know.
Any other question? No? Okay, so thank you, Hermann, for this talk. Thanks again, and hope we'll see you in Le Mans soon. Anyway.
Thank you. Have a nice continuation of the workshop. Bye.